Welcome, my name is Garrett Ginther. I'm with the Agilent flow cytometry team. I'm joined here by Charlotte Peterson from Aarhus University, and we have two reasons to be excited to present to you today. The first is obviously our new spectral flow cytometer instrument, but the other is we're also celebrating 10 years of Novasight. So 10 years ago at Cyto, we launched the Novasight system. It's an easy-to-use platform that can provide good data quality. Over the past 10 years, we've made improvements to not only the software, but the hardware, and this has all been customer-driven. So we've improved our auto-sampling capabilities. We've improved our data analysis capabilities. In 2018, we also incorporated advanced detector technology in a 1 to 5 laser platform called the Novasight Quanteon, Novasight Advanteon, and Novasight Penteon systems. And now we want to unveil the newest addition to the Novasight family, which is the Novasight Opteon spectral flow cytometer. So this flow cytometer comes in a variety of configurations, up to 5 lasers and 73 detectors. So this is a forward scatter, dual side scatter, and 70 fluorescence detection channels. So we are able to produce data with high sensitivity and high resolution, and this is due to the innovative optical design that's built into this platform. It also is very reliable. So the Novasight system in general, or the Novasight family of instruments, is really known for its reliability, and that's because we have onboard temperature control, we have electronic and fluidic sensors built into the system so that we can get reproducible results with a stable sample collection. We also are able to incorporate the Novo Express software, which is compatible with all Novasight systems. So this Novo Express software is built upon the same platform, but it adds the spectral capabilities of unmixing and reference control setups, the reference library, et cetera. And it's automation ready. So automation can mean different things to different people, but we have an auto sampler that allows for walk-away functionality. We built in a lot of automatic functions into the system, like automatic startup and shutdown, automatic fluidic maintenance at the push of a button, but it's also robotic automation compatible. So we have a universal API software that can, so far to date, we've been able to integrate with several robotic companies. So we have onboard fluidics to continuously monitor the fluid levels with real-time notifications. We do not use any fiber optics, so this is to maximize signal collection within the system. We have fluidic stability that can perform equivalently at low or high sample acquisition rates. And then we have the fully integrated auto sampler. So this does not require any change in sample tubing. There's really limited manual intervention needed. We have automatic calibration, and we can accommodate several different type of plate formats. So one of the benefits of spectral flow cytometry is the ability to analyze these fluorochromes with similar emission spectra. So what I'm showing you here is we have a sample with APC and Alexa Fluor 647. The control is up in this orange box showing distinct fluorochromes, and then down below in the blue box is showing the equivalent sample data with Alexa Fluor 647 and APC. So we can resolve these populations, and it's more or less equivalent between the two. So it's not just these two fluorochromes. We can do this with fluorochromes that are similar off of the blue laser, the red laser, violet laser, et cetera. So here is listed the similarity index for these similar fluorochromes, and you can see the data resolution down below. So if you guys want more detail on this, we do have a poster. It's number 58, and please come visit us. Similarly, the ability of spectral flow cytometer systems to remove the autofluorescence is really important for improved data resolution and accurate unmixing. So we also have a poster here showing this in a little bit more detail, but we basically have two rows of plots. The first row is unmixing without autofluorescence on the top, and the bottom row is unmixing with the autofluorescence. And I want to point you to the plots in the middle. You can see the resolution of these populations once we remove the autofluorescence from the sample is much, much more improved. And the other, hallmark of spectral flow cytometer systems is to be able to analyze these high marker panels, right? So OMIP 69 is a 40-color panel that we used as a backbone or a template to design a 45-color panel. So it's OMIP 69 plus 5 additional markers that are outlined or that are indicated with the red arrow. The complexity index is just slightly above what was published for the OMIP 69 with this 45-color panel. And this is what the data looks like. I'm not going to go into a lot of detail on this because we do have a poster and some of these plots are really small on one slide. But we are able to resolve all of these populations and more than the OMIP 69, and you can come visit us at poster number 6 if you'd like to look at this in more detail. So in addition to the fluorescence sensitivity of the Novocyte Opteon, we also have small particle sensitivity. So we used samples like the Apogee mix speeds and the NIST traceable size standards to resolve down to 80 nanometer particles from the background or the noise. So this was done with violet side scatter parameter. But there's dual side scatter options on this system. So we can analyze the side scatter not only from the violet laser, but from the blue laser. So this really allows us to look at larger particles or cells and small particles all within the same sample without adjusting any settings. So down below is a bead set that's looking at the blue laser, and this is resolving up to 15 micron particles without any effect on the small particle sensitivity. In addition, the dual side scatter also allows us to separate white blood cells from red blood cells and platelets without any lysis. So what I'm showing you here is plotting blue side scatter versus violet side scatter, and then we're able to separate out these populations without any other treatments. And one of the most, I would say, talked about or highly regarded features of the Novocyte systems is the software. We've received universally positive feedback on the software and are continuing to improve it every single iteration. One thing that people generally talk about is how easy it is to use and how intuitive it is, right? So we have these toolbars for easy to use functionality. It's a push of a button for a QC test. If you want to rinse or clean, there's no manual process here. It's really pushing a button, and then the system will go and perform its cleaning or rinsing or whatever you've instructed it to do. The software is both acquisition and analysis. So we have an analysis workspace here where you can, create all the plots that you want, get the statistics that you want, but you can also generate these reports either automatically or customized. The analysis functions that we've incorporated over the years are some of these simple ones like a histogram overlay, but some of these more complex modeling like cell proliferation and cell cycle, and then the heat map display. And honestly, my favorite function of the software, because I use it quite often, is the ability to analyze samples while you're acquiring other samples in the background. So if I set up my experiment correctly, I can run my controls first, and then I can start my analysis. And by the time I'm finished running the last sample, I can have my entire analysis done. So it's really, really convenient. It saves a lot of my time. So setting up a spectral experiment is very similar to what we would do with conventional cytometer. We would run our single color reference controls. Then we would run our fully stained sample. That would get unmixed using those controls. And then we have the unmixed data reported to us. The interface is really easy to set up these experiments with your reference control. It's really divided into 3 groups. You have your unstained controls, you have your autofluorescence populations, and then you have your single fluorochromes. This is all generated from, you can generate a list from this and add them. It's very easy to find. They're searchable within the system. And it's a very simple and easy way to set up your reference control specimen. And then once we run these, we can apply them to our library, the internal library. So right now we have a library of 937 fluorochromes. So it covers most all commercially available fluorochromes in this library, but we also have the ability to, as more and more become available, add to this library of fluorochromes. So one important consideration when running these single color reference controls is that everything is on scale. So the Novasight has been known to have this wide dynamic range that goes up to 7 logs. 95% of the time, we don't need to adjust any of the detector settings. The default or optimized settings work very well. In the case that detectors may need to be adjusted, if some signal is off scale, you'll get this easy notification. So it's this little exclamation mark on the plot identifying that some of the events are off scale. So this would mean that we would have to go in and adjust the detector settings. So we can do this in a range of ways. We can do this, we can adjust the detector individually. We can adjust detectors as a group based on the laser, and we can adjust all of them at the same time. So it's really customizable and flexible to make setting up these experiments easy. And the auto sampler. The auto sampler is it's one of the most convenient features that I've been able to use, because it can incorporate whether I'm staining in fax tubes or 96 well or 384 well plates. It has true walk-away capabilities. I generally will set up my experiments, press run, and walk away. If it's at night, I select the option to shut down the instrument after the plate is finished running, and it'll automatically run through its cleaning procedure and turn the power off. I show up the next morning, all my data is there, my cytometer is clean, and it's ready to go for the next day. We have efficient mixing and rinsing functions that can be customizable and built into the plate run. And like I mentioned before, it's automation ready. So you can store these plates into a plate hotel. Then the robot can pull from it, communicate with the system, and then you can have longer run times, and you can be running this 24 hours a day if you want. We have this optional fluidic cart that has a larger capacity for sheath and waste, and this just provides longer run times for you. So just to summarize, the Novasight Opteon comes in 8 different configurations. So there's 3 laser, 4 laser, and 5 laser configurations. And these range from 35 detectors to 73 detectors on the system. So this depends on whether you have a UV, violet, blue, yellow, or red laser incorporated. So please, if you guys are interested in more information, please join us at booth number 69 this evening. Here's a list of the posters that we have. We have 4 posters that are utilizing data generated on the Novasight Opteon. And then we have 2 other posters that we're presenting here that incorporate Novasight flow cytometry and other methods to look at metabolomics. So with that said, I want to pass this over to Charlotte Peterson from Aarhus University, and she can share you her experience over the last couple months with the Novasight Opteon.
Thank you very much, Garrett. And while we're waiting for my slides to come, I would just like to start to thank Agilent for trusting us to sending a beta instrument to Denmark. We have been very both proud and happy to beta test this instrument. So I will just briefly tell you a little about who we are, and then of course I'll show the data from our beta testing. We are from Aarhus University in Denmark. This is our building. We have labs on the first floor, and for the beta test, our microscopy core, they have some labs on the attic without windows, so it has been hidden away from everything, so all have been very secret during the beta testing. And this is my wonderful lab. I have with me Anja and Thomas. and Sune he is staying at home after his own choice. But Anya is also here in the audience. And please ask any of us for our experience. Right, just to know what our experience is with instruments, I can tell you we have a fax area 3. We got one of the first Novocytes back in 10 years ago. It's still running, and perhaps Agilent is not happy to hear this, but we do not have service contracts on any of our Novocytes instruments. We have for other instruments, but for the Novocytes, they are rock stable, so we are not paying for service contracts. Okay, we have to be honest here, right? We have an image stream. We got more Novocytes, it was the Quantions. We have a small Novocyte that's inside a GMO class 2, where the waste goes straight into a blue cap bottle, so we can autoclave the waste. We have, 2 years ago, we got an ID 7000. That was our first full spectral instrument. And we also have a Bigfoot cell sorter. And last year, we expanded with a satellite unit at the hospital with a Bigfoot sorter and a Novocyte Pantheon. So we do know these instruments, but we do also have instruments from other vendors, and we know a lot of different software and what is good and what is not good. So the beta testing. For us to beta test, we said, okay, what do we want to get out of having this option to try this instrument before everyone else? Well, we would, first of all, we are core facility. We like instruments, they are easy to use, so we can train the users, they work independently, and that they just work. Then, of course, it's not good enough just to have an instrument that is easy to operate, it also needs to perform. And for that, we agreed with Agilent. They shipped us all the antibodies for the OMIP 69, so we could test it. We thought, okay, this is a 40-color panel. We need to see the performance. How is the algorithm working? Then another thing for these full spectral instruments is autofluorescence. That's such a nice thing. All of a sudden, we can use it as a color. We can subtract it. And we have a lot of users also working with highly autofluorescent cells. So we have a user working with macrophages from mice. So we are going to show data of his cells, so you can see how the autofluorescence work on this instrument. And in the end, I'll briefly just touch upon small particles, because this is also something we have users of interest in our core facility. Right. First, the NovoExpress software that runs the Opteon. How many of you in here have already a Novocyte instrument? Just if you raise your hands, just to have an idea. Okay, so some, but not all. Those of you who already know the Novocyte instruments, the interface is exactly the same. It is NovoExpress. And I will just zoom in on the top row where they have different tabs. And the only new tab is this unmix. Everything else is exactly the same. It's NovoExpress. They just added a single unmix tab. All right, so now I would like to do set up a spectral experiment. So what do? I go to the unmix tab and I click New Reference Control. And Garrett showed this briefly. A new window opens. And, okay, one for each hand. I like to start down here for the edit. I need to tell what fluorochromes, what markers do I have in my experiment. You can either choose by laser, but I find it easy. It shows me markers from all lasers, and you type in a name. And here I had several BUV antibodies. You can double-click or use the add, and then they populate over here. And there's room out here so you can add the marker immediately. We try really to train our users well, that they should always name their markers. But still, we do have users coming to us just with a 6-color panel, and they'll have to look in the lab book, oh, Fitch is with this marker, PE, going for 40 colors. It's a mess, right? You have to name your markers. But I keep on adding all the different fluorochrome names. It populates. I got now all my different fluorochromes. I added the markers, and this is the name there will be on the axis. And this is also the names that goes to the FCS file. So when you open your data in a third-party software, you can easily see it. We had one new fluorochrome, there wasn't in this extensive list, so we went to the library, said add a new one, and you simply type in the fluorochrome name and what laser there is expected to excite it. Very easy. So what does it look like? This is running a single stain control. The software automatically, okay, I am just trying to multitask right now, makes a main gate. And when you have beads, it typically always picks nicely the beads. Here for cells, I know this marker, this is a CD159A, it's only on lymphocytes. So I changed the gate only to be gated on lymphocytes. So it's no magic, you still just have to look, does it gate on the right population? Then it automatically makes this negative and positive gate, and it shows the ribbon of the positive population. And you don't have to adjust these ribbon plots, these spectra. We have experience with our Sony instrument, and there you have to fine-tune if you've got outliers and something like that. You don't need to do that here. And like looking at this sample, this is an APC, and I actually worried a bit, oh my God, it has to be brightest on the first detector of the red laser. But by eye, it almost looks like it's just as bright on the first detector of the yellow-green. And then again, the software, it's nice. It's a nice feature. We just realized having the cursor on top of that detector, it tells you what is the median. It doesn't matter where the mouse is on the detector, it gives you the median. Okay, it's easy to read. I place my mouse over here, and the median, it's clearly lower. All right, phew. Okay, so this is the factory settings. It's all good. And of course, you can go down to the same detector of the UV, and that is much lower. I could see that by eye, but looking over here, I would worry a bit. Did I have the strongest signal in where I expected? And yes, I did. Okay, ease of use. Setting up an experiment, the software is, those of you who don't know the NovaExpress software, it is truly the easiest software we have worked with. Naming samples, it's easy and it stays. Whenever now I look at plots, I have all the names. Gating, you can place all the different kind of gates you would like. When you make quadrant gates, it gives you the names you have on the axis. So it's not just R1, R2, R3, R4. You need to rename. It does that, the correct names immediately. And what I like most, I think, is the multitasking. That while it runs samples, you can start analyzing a sample that have already been acquired. While it runs your single stain controls, I can go back on the ones it already have been running and checking it did gate on the correct beads or the cells, whatever I'm looking at. And also a thing like the automatic shutdown, it has all the cleaning solutions on board, so you can press shutdown, close the computer and go home. That is actually a really nice feature. Okay, now you need to see some of the unmixing. I think this is what you all are curious to see. So first thing, we would like to test the OMIP 69. So we of course read the paper. The OMIPs are wonderful, and we read the supplementary, and we could see there were some fluorochromes where the spectra looked different, whether we looked on beads or cells. So we thought, okay, this is actually where we need to start. So we ran these fluorophores on beads and cells, and now I will just first show you two examples, the BUV 661 and PE Psi 5. This is my beads, and with beads, of course, you get a very strong signal, a very nice ribbon. This is cells. Well, this is a CD39, and there's not that much on the surface of my cells, but this is the ribbon I get. Kind of can appreciate it's the same shape, but it's not as clear as on beads. So importing these to the library. Up here, I got CD39 on cells and CD39 on, I have it both on cells and beads. And I'll show you the cells first. This is beads. Now I'm flipping back and forth. If you look here on the primary emission, it's exactly the same. But for the secondary and tertiary emission, there is a difference between cells and beads. Right, so there's a difference. All right, I need to acknowledge this. Then for PC5, now I will start again with cells, and now I show you beads. You hardly don't see any difference. Perhaps try and look down here. Oh, sorry, it was the wrong way. There is perhaps a small change, but really not much. And here I must say, this is I had only very few comments as a beta tester for the software. This is one of the wishes I would like to be able to overlay these plots, because it makes it really easy also if a tandem is broken. You still cannot do that. What we have done here is plotting two plots on top of each other where one of them is semi-transparent. So just to know, I have told Agilent this is what we would like, because this is very useful. But PC5, it looked exactly the same on beads and cells. So looking at these, I had 4 fluorochromes. I couldn't see a difference. These 2, I saw a bigger difference. And these 3, I make them lighter red. There's a smaller difference. How big a difference is big? When do we have an issue? I don't know. And I guess it might be different from each instrument and each unmixing algorithm. But we started with this. All right. Then I have to start saying we had to make a few deviations from the OMIP. And the first was CD4, CD24, and CD25 were in back order. We tried both from the States and from Europe to really push the distributor, but we couldn't get them. They were going to arrive tomorrow. We couldn't use that. And to test this panel, CD4 is really crucial. I said, well, it doesn't make sense. We are not doing this without CD4. We have been testing this real yellow from BD 610. We could look in the spectra. It could fit in. So we had no clue if it was going to work, but this is what we tried, because I really wanted a CD4 in the panel. And in the OMIP, they stain in 1 round. I didn't feel happy about that. So I talked to Agilent and Pei Fang, sorry. And she shared her staining protocol. She stained in 4 rounds. So all the chemokine receptors I did at room temperature first, and then the next 3 rounds were cold, and I did wash between each round of staining. And then I will say this is not a disclaimer. This is just how we did it. We used the factory settings. When we ran the fully stained sample first, just to check we didn't go off scale. We didn't go off scale. And then perhaps I thought, okay, perhaps we could have spent a week or more time to try and optimize. But I said, okay, let's just try. So what I'll show you is on the factory settings. And even though I showed before there's a difference between beads and cells, the spectra, I really like compensating on beads, because they give you always a good staining, and some of the markers in the OMIP, they are rarely expressed. So the unmixing I will show you is done on beads, except for these 2. This one is a Miltony reaffinity antibody, and therefore I used the BD compensation beads. It didn't bind. I should have noticed that before, but it was first when I saw a blank staining, it was like, oh, okay, it makes sense. This one was a human mistake. I must have pipetted air. I was really trying to pay attention and pipetting well, but there was no staining in my bead. But we did the staining in parallel for both cells and beads. So for these 2 fluorochromes, it is cells. And then again, the Novocyte software is easy, because I had a huge specimen with all the single stain for beads and one below with cells. So for these 2 where my bead staining didn't work, I simply went and copied the events in my cell sample and pasted it in where my beads should be. Then, together with all my beads, I have these 2 where it's just cells. And on cells, I have a nice staining. Right, so the software saved me. I could have gone back to the lab and did another staining, but let's see, the software can do this, right? So, first one, I'm running beads. That was most of the samples. This is my single. It automatically makes this main gate, it calls it, gates on the negative and positive. And I have my ribbon. It all looks good. And right now I'm looking at the raw workspace. There's a tab next to it, the unmixed. When I click the unmixed tab, then I see this was the BUV 496 something. I see that against every other color I have in my experiment. So I can immediately see, does it seem okay? Yeah, I think the unmixing looks okay. All right. After doing that for all, now this is a 38 color experiment, it's busy, right? But I can see all the spectra, and now to the data, right? And this is done one. We have done this only one experiment, and since it worked, it's like, okay, we're good. So, and I think actually I will put the OMIP, copy-paste from the OMIP, so we can compare with that immediately. So I tried to do it exactly as they did, but you know, it's really difficult to behave. I really like to look at time versus a fluorescence parameter. So the time plot looks different. They looked at forward scatter, I'm looking at CD3. Okay. Then for the singlets, on all the novocyte instruments we have, the monocytes have a different angle, a different shape compared to the lymphocytes. So this is very normal. It's not my doublets. If I get these away, I have no monocytes. You don't really see that down here. I gated live cells. I had a few dead, not many. The CD45, monocytes, lymphocytes. And here the nice shape of the different, the classical monocytes, the intermediate, and the non-classical. Looks very much the same. I'm very happy. We are moving ahead. Then the main gating for the T, NK, and B cells. The NK, the CD56 dim, the CD56 bright. Among the CD3, and this is where we have the different dye. This was this CD4 real yellow 610 that wasn't in the OMIP. This is the OMIP color. Yes, true, the OMIP has a better separation between CD4 and CD8. My separation is not as good, but I can still separate CD8 versus CD4. Then among the, oh yeah, and all of what I'm showing here is screenshots from the NovoExpress software. So it tells me all of the time what have I gated on: singlets, live, CD4, lymphocytes, CD3 negative. All right. Then CD19 versus CD20. These are my B cells. Among the B cells, CD27 versus IgD. And among the IgD negative, I'm looking at IgG and IgM. Okay, so here, this was the first. So far, everything is good, but here you could say, all right, is the unmixing, perhaps this is a bit over. Okay, now usually we would say overcompensated. Is it over unmixed? I'm not sure. What do we call it now? And here perhaps a little. So undermixed, yes, good, thank you. So if all I'm going to show you is I haven't touched anything, but just to show you, if you are unhappy, how it works here in the software is you can add a compensation on top. You can say, do a quick compensation, and correct me if this is wrong. You're adding a compensation on top of the unmixing. So you can use these sliders, and you can get it to look like the median of the positive is the same as the median of the negative, right? It is possible to do, right? But I thought it was most fair, so the remaining, I just removed this again because I could still gate my populations. Now we're going to look at the CD4 cells. And I will just compare with here. We are looking at CCR7 versus CD45RA. And among the double positive, we get the naive CD4 cells. Among the, let me see, it's the RA negatives, CCR7 negative, so it's these guys. We get the early effector. And look, very nice separation. And these guys, we have the central memory. And among the central memory, we are looking at CXCR5 versus CXCR3. And here I must say I was really impressed. We are out in the very long wavelengths, and look at that separation. That was really amazing to see. So the detectors are definitely performing. The unmixing is pretty, and this is the APC87, so this is also in the long wavelengths. The separation is really, really good. That is where other instruments struggle to get good detection out in the long wavelength. For the CD8, I will go over this briefly because it's the same markers just for the CD8 cells. And again, the unmixing is good, the separation is good, I'm very happy. This is some of the extra CD8 markers. This is the PD1 versus CD95. This is the lower row is for the double negative here, and the top row is from the double positive. Here we have CCR5 versus CCR6, some of the sometimes troublesome chemokine receptors. Beautiful pattern. And the CXCR3 versus CD57. I find the populations there make sense with immunology eyes, and it looks pretty. The innate leukocytes, or innate lymphocyte, what are they called? The innate lymphoid cells, sorry, these ILCs. They are negative for a lot of things. Negative for CD3, they are not B cells, they are not monocytes, they are not CD133. And again, compared to the OMI, you get the cells you are expected to have. And this is the final one I will show you. I have more of all of these population in some extra slides if you'd like to see afterwards. For the dendritic cells, you gate on these, the double negative cells. And then you pick the HLR-DR, they should be positive. Again, this is a PE Fire 810. Beautiful separation. And here we are looking at CD123 versus CD11C, and look at the two colors. This is, here we have the super bright, sorry, I had to remember if it was star bright or super bright. It's super bright, 436 versus E-fluor, 450. You can see the shape of the negative. The colors must be very similar because it gets this funny shape. Indeed, they are very similar, but it separates beautifully. And just to compare with the rest of the OMI, I can find the cells I expected to. So on the performance side, I am truly impressed. We did this one experiment. We used beads to compensate except for 2 fluorophores. And this is just, I have done no adjustments to any of the ribbons. I am truly impressed. Okay, then autofluorescence. And I forgot to subtract autofluorescence on all of what I've shown you. So all of this is without autofluorescence. And then my excuse was, oh, it's mononuclear cells. They're not very autofluorescent. So I'm going to look at autofluorescence on some cells. There's highly autofluorescence. But all of what I showed you, I didn't even subtract autofluorescence. Right, autofluorescence. This is where we also added all the colors to make in your spectral experiment. There's here you can add autofluorescence, and you can add multiple colors or multiple autofluorescences. So for the mononuclear cells, I'll just show you what it looks. This is without you subtracting autofluorescence, and this is with. So, of course, using the autofluorescence, it makes it nicer, right? We can all agree on that. So it's great we can do this. Then, where we have the challenge is our peritoneal lavage in mice, where you get all different kinds of cells. Lymphocytes, monocytes, granulocytes, eosinophils, and macrophages. And I have and a forward side scatter of this. It's a bit more messy than what we normally look at. So we have the lymphocytes, we have the eosinophils, we have the macrophages, and the granulocytes on top. So, and the researcher, he's mainly interested in macrophages, but he also liked to get numbers on the other cells. So we tried to play a little with the autofluorescences. We gated on lymphocytes, one on macrophages, and the software, by default, it always calls one of the gates main. So I guess I could have renamed it, but the granulocytes are now just called main. This is the spectra from the lymphocytes, this is the macrophages, and this is the main, or my granulocytes. So if we just go back, they are slightly different, but it's easier actually to add them here. Here I added all 3 of them, and I'll show you in the library just in a moment. For the experiment, I actually chose only this one. and I will show you what it looks like. This is our researchers' 18-color murine panel, mainly for macrophages. And if you look here, he is doing this panel on our ID 7000. So he is smart, he knows this is where my autofluorescence is. He doesn't have any marker of interest in that area. So here we have the 3 different autofluorescences of the lymphocytes, the macrophages, the granulocytes. They are very similar here, but in this area, it's these 3 lines. There's a difference, and also over here, whether it's a lymphocyte, a macrophage, or a granulocyte. Perhaps if I change, this is when I just use this one single autofluorescent gate, you can see it changes over here, but not much here. All right, so let's look at the data. We gated on cells, removed non-CD45 cells, removed dead cells, gated on single cells. Then it's a CD19 versus a CD11B. So he picked out all the different types of B cells he has in the peritoneum and the non-B cells. Then he removed the T cells. We're looking at these. Okay, and now we're looking at NK cell marker. We are removing these, but look here. This is most likely I'm not doing a good enough job with my unmixing, right? This is the macrophages. They look clearly over unmixed. Okay, and over here I'm just removing the eosinophils. But let's focus on this one. I noticed this, and then in the software there's a button called End-Time End Plots. You click the button, and you get all your End-Time End Plots. It's so nice you don't have to do that, right? First I looked, and I couldn't find my autofluorescence. But now I zoom in. Up here, it has a tick mark saying hide autofluorescence. It is ticked by default. You just have to deselect it. When I deselect it, then I have autofluorescence on the x-axis on all these plots. Oops, and when we look here at the first, this is indeed my NK11. This is where I have my issue, and you can see, oh, it's clearly over unmixed. So when I turn on the compensation, just adding this one actually fixed a lot of problems in the unmixing, if I go back and forth. So from looking like this, it now looks like this. But this end-time end plot, again, the software, it's just nice. Right, we need to see his macrophages. Could he find the one? So he's now looking at CD105 versus CD11B. And these are different macrophage. I'm not a macrophage person, but he could find all of his populations, the unmixing. It's really nice. This live one in PE actually typically goes off scale on other instruments for him, but because of the large dynamic range, it wasn't off scale here. So it definitely also works on highly autofluorescent cells. I am running out of time, and so just a little bit about small particles. You can add, if you want to do small particle analysis, you can add a 0.05 micron filter to the sheath inlet. So it gets filtered before it reaches the flow cell. This is standard 8-peak beads. And we did a gaintration. And here I would just like again to say, to do a gaintration in Novo Express software, you just turn on all lasers and adjust the gain. We did with 20% instead of 50%. So all of these are all run from well A1. Then we run once. We say, OK, go down from the factory settings 20% and so forth. So this is the default. Here we are below default. And this is if we go higher. We wanted to find the optimal settings for looking at small particles. We did this for different detectors. Here's from the violet, the yellow-green. And then we gated on peak 1 versus peak 2, and we did a stain index for all of the detectors. And what I show here is the best stain index for each detector and what gain it should have. And we have highlighted, these are the 3 plots I showed you on the previous page. This is the stain index, and also this is the maximum gain we can go to. So for sure, there would be some detectors where we shouldn't go for looking at small particles. We should go where we have the best stain index. And we had prepared this to use the Sigma exosome GFP-labeled particles, but they didn't arrive in time. So this is just, the blue is buffer, 100 micron polystyrene beads, 200 and 500. So, but it was what we had time to play with. So thank you for listening. And now I'll be very happy to take questions.